It's Friday, and Fridays it's the AWS Developers Podcast in all your podcast application. Today we're talking about AWS Lambda Snap Start. You never heard what it is? Don't worry, we are going to explain everything. Good morning. Thank you for listening to the AWS Developers Podcast. You can subscribe to receive new update every Friday morning in all your podcast application, Apple, on YouTube, with video, on Deezer, Spotify, and all the good podcast application. All things that matters for developer. Today we are going to talk about AWS Lambda and one very specific feature of Lambda that we introduced like 2 years ago, something like that. It's called Snap Start. And I found on social network and on his website an expert to talk about Snap Start because you did so many tests and benchmark about that. It's amazing all the tests you did around Snap Start. My guest today is Vadym Kazulkin. Sorry, I will repeat that. My guest today is Vadym Kazulkin. I hope I pronounce your name correctly.
That was
You're
correct.
the head of development at IP Labs. Thank you for being there. You're going to explain in this episode all the tests and the benchmark and your advice to use a Snap. It's super complicated to pronounce that name. Snap Start. But maybe just explain us what is Lambda Snap Start.
Okay, first of all, Sebastian, thanks for inviting me. It's my pleasure to be here. So let's start with the problem statement. Currently, Lambda Snap Start or AWS Snap Start is only available for Java on Lambda, so not on containers,
Lambda function.
not on ECS, so it's only Lambda function. And the situation is, even if maybe call starts become less and less the problem, because many applications might be asynchronous, or there is even now stuff that AWS pre-initialized, so the call starts happen not so frequently, but still there are applications that require synchronous communication there the overall latency matters. And of course, Java as a language...
So maybe I interrupt you. Maybe what is a call start for Lambda function? Let's start from there.
So the call start is... So Lambda is a function as a service. That means that one request is only executed on one environment. In case of Java, it's then JVM, Java Virtual Machine. And in case the environment is already there, then it's easy, then only the handler function, the function code itself will be executed. But if the environment is not there, for example, we deployed a Lambda function for the first time. We developed some new Lambda function, and then that's the very first invocation. And then there is no environment. And what is environment? The first thing is it's Firecracker VM. That's a development done by AWS, with just Firecracker VM. Then in case we use Java, JVM will be starting. And then the class that we declare as a Lambda function needs to be loaded. In case of Java, the static initialization, so the code and classes around this handler function needs to be loaded. And as a first step, even the function code needs to be downloaded for the new environment from S3. So all these additional steps, like starting the environment, downloading the code, starting the JVM, do the all static initializer stuff, and maybe if we use some frameworks, there will be some other stuff like annotation processing. The people who know Java knows this. These are all part of the call starts. And the warm start, in case the environment is there, is only the function handler execution. This is kind of how it is there. So call start happens once again for the first time.
Yes, and call start happens for the first time after you deploy your Lambda function, but also in case we need to scale. Like you have 5 micro VM already started, and there is 10 requests arriving. We need to create 5 another micro VM, so there is another 5 cold start for these environments.
Of course, that's another use case, and of course, AWS needs to balance what environments are there. So in case then we just needed 10 requests, and then we have for time being only 2 requests per second come, AWS will shut down the environment, so they cannot stay warm forever. So if then number of requests goes down, then AWS will relocate this environment, so kind of remove these environments. And of course, AWS needs to patch the environments from time to time for security reasons. So even if we have steady workloads, I would personally expect that after several hours, anyway, these environments will be kind of shut down because of the security
Shut
reasons, and
down.
then basically the new ones will be started. So
Cold start is a recurring problem on AWS Lambda, or challenge since the beginning of Lambda. It's getting better and better for different reasons. But Snap Start was specifically developed to address that cold start problem for Java environment.
it's not only Java which suffers from the situation that the cold starts take long time in Java because it's interpreted language and all this JVM. It's not just kind of is there and you can use it. So class loadings, all that stuff, it takes time. JVM start, it takes time. It's not Node.js, it's not Python, where it's much quicker. And of course, even, for example, I measure in many use cases, you experience only cold starts for synchronous application. It's more important stuff because it's kind of it's
with low
important
traffic.
to have. Yeah, it's just where the latency matters. It may be even less than 1% of the invocations. It depends on your traffic pattern, of course, but it may be even 0.1 until several percent. But still, we know all these measurements that the people may jump out if they don't receive any response for 1 or 2 seconds. Even Amazon did that on their own site, so we know that it in fact it's about business. Yeah, and even if it's only 1% cold starts and 1% of those people will jump out, it may impact your business. It's of course experience. And in serverless architectures, there are many small functions. So if many functions experience constantly these cold starts, and the whole experience may kind of break.
Yeah, but that's a well-known study from Amazon.com that says for every added milliseconds of latency on Amazon.com on your shopping basket, there is a percentage decrease of purchase. And we can really measure that. And it's a matter of milliseconds. It's incredible. I'll try to find the paper and link the paper to the notes of the podcast. So Snap Start is there to reduce the cold start for Java environment. How does it work behind the scene? What did we change?
So how Snap Start works, it's the Snap Start is the technology for creating the environment snapshots and then restoring them. By environment, so I mean Firecracker micro VM will be completely snapshotted. And then it will be restored.
Instead of creating a new micro VM, we take like a memory snapshot complete of the VM, and instead of recreating one, we restore it from the snapshot. That's pretty much like we can do on the VMware desktop or the virtual machines that are running in our laptop a few years ago. We could either stop the virtual machine and restart it. It takes a long time, or we freeze the virtual machine, we pause it, and we restart it. It's much faster. Is it a good analogy?
Yes, of course. It's everything will be snapshotted. VM memory, read-only disk, read-write disk, VM state. So basically, the whole environment. Yeah, it's not only the process, and this is the whole execution environment, which is then
environment
Firecracker micro VM in this case. And the most important thing, how AWS did it, in case we enable Snap Start, which is more or less checkpoint on the Lambda function, on per Lambda function. It's our conscious decision to enable it or disable it. In case it's enabled, then the life cycle of the Lambda function will be divided in 2 phases. So for the deployment phase, in case we enable Snap Start, then the separate worker will be started where the kind of the cold start phase of the Lambda function will be run. So the worker starts JVM, starts the Lambda function, and does all the initialization work, but without invoking the Lambda function itself. So this is all cold start phases will be run, and then the snapshot will be taken. There are optional hooks which can be used for priming stuff. Maybe we'll be talking about. There is pre-snapshot hook, and then also post-restore hook. Yeah, but this phase on this the snapshot will be stored, and it will be stored in the how we know AWS kind of it will be encrypted and then stored in each availability zone of the region where the Lambda function runs. So in case the region is not available, then the snapshot can be kind of later restored from another availability zone. So this is the snapshot taking phase. Of course, this phase will be longer due to the snapshot phase. So I measured this. It takes more than 2 minutes additionally for this purpose of creating snapshot, encrypting it, and storing it. If we deploy many Lambda functions in the same time, which is in many cases the true condition, then the snapshot will be taken in parallel for all the functions. So it will not be too much longer only because we deploy 10 functions. But anyway, there is kind of a bit developer experience, which is, this is the waiting time that comes on top.
When you deploy a new function, and only for a new deployment.
For each new deployment, for each change. Also, in case then the Snap Start is enabled, and then the real traffic comes, then the invocation, in case of the real world invocation, then there will be no normal initialization, but only the snapshot will be restored. This is in case Snap Start is enabled. It's simply restore the snapshot and then do the invocation. So of course the promise is that the restore will take less time than the normal call starts. Otherwise, it simply doesn't make
faster.
It doesn't make any sense. So basically, what I measured, I took kind of classic serverless application with API gateway, Lambda, and DynamoDB for creating, updating the products. This simple application has the size of roughly 18 megabytes because of dependencies, which is important because the size of application also the factor how long the call start takes. Without Snap Start, because the code needs to be downloaded, more things needs to be loaded in Java. Also, the bigger the application generally, the bigger the call start. So if we forget the Snap Start, then first the call start takes, so the call start takes for P90, so percentile 90, roughly 3.5 seconds for Java. So this is what we
for
need
that application.
This is for this kind of application. Roughly, maybe depending on the minor version of JVM or whether we use Java 17 or 21, but this will be something between 3 and 3.5 seconds only for the cold starts. The warm starts are really quick in Java. So the Java is very quick programming language, so the execution is not a problem. So basically, only by enabling the Snap Start, which is checkbox, I was able to go down to roughly 2 seconds. So from 3.5 to 2 seconds of the call start, only without doing any other work as besides enabling that. But it's of course not the end of the story. There is, as I already explained, these hooks, pre-snapshot hook and post-restore hook, and especially post-restore, pre-snapshot hook is really important because it gives us the possibility to do some additional work. And what can be this work? For example, load as much classes and do as much as initialization as possible so that this becomes part of the snapshot. And then on restore, less work needs to be done. So what it can be, especially in this classic application, it requires a bit of knowledge, but it's repetitive knowledge and it becomes a common knowledge. What are those things? So the first one, if we talk to DynamoDB, behind the scenes, this is the HTTP client, because the invocation to DynamoDB is a HTTP call. And the initialization of this HTTP client, which is in case of Java by default Apache client, we don't need even to write something, it's already packaged. This is a Apache client, and it takes several hundred milliseconds for the first initialization phase of this HTTP client. So we can pre-initialize that once before the snapshot taken, and then we will save the time. Another thing which is important to know, DynamoDB is a NoSQL database, so the JSON will be stored there. But with Java, we have Java objects, and they need to be converted to JSON. This is called marshalla, unmarshalla, serialization, deserialization, all these are synonyms, basically. And for that, we use some libraries that do this serialization, and they also take time for the first initialization. By default, it's Jackson, Marshalla, but that's the same. So basically, what I can do, I can simply fake the call to DynamoDB. In my case, example, it was get product by ID 0 from the database. I don't even need to have this product, but by talking to DynamoDB, for the first time, I will pre-initialize HTTP client, and I will pre-initialize JSON, Marshalla, or unmarshalla, depending if I'm writing or reading something. And this technique is called priming. I pre-initialize stuff. There may be something else for your application, or if you don't use DynamoDB, then there is sometimes you cannot prime. But if I do this priming, I can gain additional benefits.
So let's recap what you said. If you use a Java snap start, so a snapshot of the virtual machine of the micro VM instead of a cold start, with your benchmark application, you observed going from 3.5 seconds of cold start to 2 seconds. And I made the math while you were talking. That's 42% reduction of time, almost 50% reduction of time. So it's significant. But then you said you can do further optimization. So you can preload a couple of Java classes before the first use. So not wait for the first call of the Lambda function to load them, but load them before the snapshot, so that these classes will be loaded into memory when the snapshot will be restored. And you give two examples. It's the Jackson class, so the class to do serialization of a JSON object in Java, and the HTTP client. So my question is, when do you do that? You cannot do that in the handler call of your Lambda function. So there is another method that is invoked before the snapshot. How does it work?
That's exactly. So these hooks are implemented by so-called crack API. It just doesn't matter what it is, but this basically we need to implement additional interface in the, for example, Lambda function implements the interface resource, which is exactly, and it gives before checkpoint and after restore methods. And before checkpoint is exactly the place where I will put that code that I was talking about, and it will be executed before snapshot. And after restore, basically after restore, but in that case it's mostly empty. There are use cases that's important, for example, restore connection to the relational database if one uses that case. But in case for DynamoDB, I really basically use this before checkpoint. And what I also saw by calling this get product by DynamoDB, all the classes that are in the chain of invocation, because I'm using AWS Java SDK, DynamoDB stuff. There's a lot of chain, everything, the whole chain until the code, until the stuff is invoked from DynamoDB will be preloaded. And this is kind of also, this takes time to load all the stuff. So that's kind of the benefit.
And what's the benefit you observe by using this priming technique, by caching as much of the class loading as you can before the snapshot? Because in your benchmark, you did measure the cold start, the snap start, and then the snap start with priming. What's the difference you're observing there?
So if I look once again at P90, having snap start and priming, this kind of priming that I explained, I will have cold starts of something between 800 milliseconds and 1 second. So it once again significantly goes down. Yeah, we are then talking about cold start for P90. So for P50, it's even less. We are talking about less than 1 second. So it will be probably something like more than 70% gain comparing to not using snap start at all. And it's really significant in this case.
Just to be clear, P90, for the ones that are not versed into benchmark and statistic, it means that 90% of the requests complete within that time that you give. So it's the normal behavior for 90% of the request or less.
Yeah, it's okay. Exactly. I look basically on P90 because it's P50, it's just only 50%, but P90, 90% of cold starts. It's something that's worth noting. Of course, I measured P99, P99.9 max. All that stuff can be found, but I cannot call all numbers. Probably very difficult to follow. But P90 is something that
you're going to lose everybody if you do that. No, P90 is very representative. It means 9 requests out of 10 will start within or will be served within that time frame. So let me repeat: 3.5 in cold start, 2 seconds with snap start, and 1 second, or even you said 800 milliseconds, so below 1 second with the snap start and the optimization that that is called priming. Exactly. So you did all these benchmark and you wrote a blog post in 26 parts, so it's incredibly detailed. What is the type of information? Why are there so many different parts? What is the type of information you share into that blog post?
So first of all, as Snap Start was announced, and it was around reInvent 2 years ago, so reInvent 2022, it was Java 11 there. So I started measurements with Java 11. Then a year later, Java 17 was released on Lambda, and then Java 21. And of course, there is JVM impact. So I remeasured basically the stuff. But what else? Of course, I measure this with different memory settings. What I forgot, I gave Lambda function for this sample application by default 1 gigabyte of memory. But of course, I would like just to measure what will be impact on warm and cold starts on both, because it's trade-off. For example, if I give only half of the gigabyte memory or up to 2, it's cost performance trade-off. So I measure this for all cases, without snap start, with snap start, without and with priming. And that's one dimension. Another dimension is using different Java compilation options. That may be too complicated, but basically, of course, there is a trade-off, because Java has different compilation options, like with too many optimizations and with less optimizations. All this optimization take thread and take RAM, and they are not always, so they are developed basically for long-living applications, and Lambda is short-living applications. So it's important to find the balance so that the Java, the normal execution is not disturbed by all that optimizations. Sometimes they kick in only after 10,000 of Lambda invocations, which may not be the case because the environment will be destroyed before 10,000 invocations. So there is no sense in these optimizations. They are for long-living applications once again. So I simply try to find the balance, to find what Java compilation will be good. And there are some interesting stuff around that. This one dimension, this was the second one. I tried different HTTP clients. So the default one is Apache HTTP client, but there are 2 others that AWS support. Another one is also URL connection HTTP client coming from Java world, but AWS also released their own AWS CRT HTTP client, which is better suited CRT for better suited.
So
for
CRT means common runtime, something, common runtime. So it's a common base of code which is shared across many different SDKs, and it's written in C, so it's supposed to be native. Super effective.
Yeah, it's native code. First of all, the asynchronous client was released, and in this year, synchronous. So I measured all these 3 ones and also find out that AWS CRT produces the best result. It was really measurable without snap start and priming. Especially with snap start and priming, I already preload the HTTP client, so the effect is not so much. But in case you can't apply priming, it's then significant what AWS CRT produces. So in terms of going down the call starts.
And it makes sense, because what takes time for Java is not really the execution. Java is a very fast language as well. It's really the time to load the class. So when you compare CRT in C and the Apache HTTP client in Java, what takes time between the two is loading the class. So with the priming, you avoid the class loading, and at the end you have roughly the same performance between the 2 HTTP clients. Intuitively, I would say, yeah, that's what I expect from the benchmark. Just one question: how did you run this benchmark? I guess you wrote code to automate the compilation, the deployment, running the tests, and collecting the result. You didn't do that by hand.
Of course, but maybe I will add some more dimensions to answer, and then I will answer this. So there is, of course, also asynchronous invocation. DynamoDB supports asynchronous clients, but this turns out completely application needs to be asynchronous. So you need to rewrite a lot of code, and not everybody would like to have completely asynchronous invocation. And the last measurements that I added, it was using different Lambda architectures. Default one is x86, but there is also ARM64. And since July, AWS added support for snap start also for ARM64. So before that, I could only use snap start on x86, and that's why ARM was not interesting for me, because snap start optimization did not work. But now I could measure this, and ARM is roughly 25% cheaper from the memory perspective. So there was a trade-off also. There is a pricing model for Lambda, which doesn't do anything with programming language, but kind of duration memory effect of ARM, first of all, is kind of 25% cheaper. It runs on Graviton, which is also AWS own stuff, and that's why it was cheaper. And it was interesting also for me to find out how it will behave then with cold starts having ARM, for example. So that's why.
What is the best combination? That explains the 26 article with all these dimensions. Yeah. According to your test and your specific application, it's important to say it's for that specific implementation. What is the best combination? The combination that produce the best result in terms of cold start or warm start?
Basically, it's very interesting question. So I will stick to 1 gigabyte of memory using x86. architecture. Default compilation option, default garbage collector, I will stick to that. I will use AWS CRT HTTP client. It provided the best results. With ARM architecture, what I measured, I had 25, roughly 20% bigger call starts with 1 gigabyte, but it's 25% cheaper. So personally, if I will use ARM architecture, I will give Lambda more memory, a bit more memory, so I can put down a bit call starts, but it will be in the sum probably cheaper than using x86. But I will need to give more memory if I would like to reduce the call starts. These were basically my expectations. But the interesting stuff, well, it's not only about call starts, it's about warm starts. And for example, using ARM, I had only 8% slower warm starts for 25% less price. So once again, giving more memory, I can then bring them also down. So the price comparison, so ARM gave for that specific use case, I would say I will try to tune that with ARM. Java is run once, write everywhere, so I don't need ARM architecture to write the code. It works exactly the same. It will be only executed after the compilation on ARM. So this was basically their result, or the best combination.
I took a bit of note. So you said that the call start / snap start time is best with x64, but if you increase a bit the memory and so pay a bit more per millisecond on ARM, you get equivalent result with ARM. And because ARM is much cheaper than x64, at the end it's still cheaper, even if you are using more memory. And for the warm start, you said ARM, I took note of 8% slower than x64, but for 25% less of the price. So it's still a win-win on the price-performance ratio, which is aligned to the AWS messaging as well, saying that ARM has a better price-performance ratio. We're not talking just about performance, but price-performance there.
Exactly.
That's a super interesting benchmark. How did you develop that benchmark? What is the tooling you developed to automate all that?
It's not very difficult. So I basically need some kind of load testing. You can take artillery, you can take Fiddler, Apache JMeter, it just doesn't matter. What I did, I deployed the application and simply I use Hey tool. It's open source. It works like curl. That's simply API gateway call, HTTP call, and the parameters look, but I can say how many containers and how many executions per container per second and how long does it take. So I simply put a lot of load for 1 or 2 minutes, then I made a bit pause, then I executed it once again and something like for around 1 hour. So with that, I had 100,000, roughly 100,000 warm starts and something between 1 and 200 cold starts was that time. So with the pause, I achieved that the containers will be removed completely and then needed to be started. So I made the pause of 6-7 minutes, and for my observation, it was that after 7 minutes without invoking anything, all containers are gone. So basically the next executions will be cold starts again. And as I put a lot of load, as you can see in 1 hour, more than 100,000 warm executions. So it was kind of, for me, representative enough just to measure both cold starts, warm starts, concurrency of Lambda functions. It's basically Hey command around a bit of bash. Just put pause for cycle, more or less how many cycles I would like to run. So very, very simple stuff can be automated with Postman, all other stuff. I know people use artillery for this. It simply just doesn't matter. Of course, it doesn't reflect the invocation pattern of all applications. So if you would like to measure for your case and you know better what's your pattern, like can be steady and then for 1 hour and then once again steady, then you can incorporate that better. Then you see what does it mean. How it's important even to know with your pattern how often will you experience cold starts. For me, it was 0.1%, but I know there will be much different cases that might have 1-2% of the invocations, especially
depending on the
spikes,
on the traffic pattern.
Traffic. If you have frequent spikes and big spikes, then for sure, and during that spike, you will experience higher rate of cold starts, and you don't want to lose the people, especially with that spikes. You will probably make money there, and you would like just to have normal latency. or at least not so much increased.
The best response time when you have a lot of customers using your application. How did you collect the metrics, the call start time, snap start time? So all these data are in CloudWatch, but you had to fetch them and to analyze the CloudWatch?
Yeah, that's pure CloudWatch. AWS publishes the queries. They are completely different for cold starts and warm starts, depending whether you have snap start or not. There are different metrics included, like restore time, which is not the part if you are not using snap start. So this information is available, and it's also on AWS pages that describe snap start and how to collect metrics. That's also available at least in the early articles of the snap start series, and then simply stopped copying them because they are this public knowledge. But it's pure CloudWatch, producing metrics and simply writing down the results.
And I will put all the links in the notes of this podcast. So if you're listening in a podcast application, just scroll down the page and you will have the link to to the queries, of course, to the 26th article of benchmark from Vadym as well. There are a couple of caveats. The reason why AWS did not apply snap start automatically for all Java functions, it's because it's not suitable for all use cases. So can we talk also about the case where developers should not try to use Snap Start? What are the challenge with Snap Start?
So basically, there is no challenge per se. I didn't find it, but of course, maybe if you do some simple computation with your Lambda function, or not too much class loading, you may find out that the results are with and without snap start are quite close. For example, simple hello world, which nobody writes, you will have roughly the same half of the second call start. There is no class loading, nothing is to be done, there is no calculation, write the same string. Then the both values are the same, and with snap start enabled, you will have 2.5 minutes of additional deployment time. So there is no sense in that. Of course, you need to measure the effect of snap start, but you need to think, can you apply priming or not? Because with priming, you have the best results, but of course, not everybody is talking to DynamoDB. And so you need to think, can I pre-initialize something? So preload classes will generally help. So basically, I experience maybe if you are on the staging environment, you would like to test whether the code is working that you are doing, then maybe don't enable snap start just for quick deployment phase and check. So if it's about I change something, I would like simply to make some tests, then it might be quicker. Of course, in some point of time, you need to think about measuring performance, and then in that case, you can activate it. It's one line in all infrastructure as code tools that are there, SAM, CloudFormation, CDK. So that will be kind of what I have discovered kind of as the best pattern.
I remember I read something from one customer that was using Lambda to generate cryptographic keys. Like the call to Lambda was generating a key, and you know that to generate a key you need a random number, and the source of randomness is most of the time coming from the operating system. And because it's not a new micro VM for each container, but it's a restored container, the seed for the randomness was identical between all the calls because it's coming from the same machine. And the customer was saying it reduced a bit the cryptographic strength of the key for that specific use case because it was relying on the randomness source from the operating system. Did you hear similar complaints? Did you observe behavior that are specific to the fact that we restored a snapshot and not create a new micro VM?
So there are, of course, some cases. For example, if you have connection to relational database, so there are some issues. So one of the interesting cases that, for example, is known is it's dangerous to use time-based caches. For example, if you store something for 10 hours, the reason for that is, of course, you store it for 10 hours, but the restore can happen right after or after 11 hours. So the value may be there and might not be there. It might not be a problem. You can fetch it and cache once again, but basically time, you cannot rely on that. You mentioned now the very interesting part with uniqueness and randomness, uniqueness. And it's very interesting because what AWS does, and it also influences measurements, the snapshot is stored in the low-level tiered cache. And this is amazing technology, if I am allowed to explain about what is there, how it's created, and what
Yes,
did it
please.
take. So basically, as I said, the snapshot is stored on S3, but the snapshot can be for function which is 1 GB of size might be several gigabytes. So the question is, if you will fetch the snapshot of several gigabytes from S3 directly, then your cold starts will be much worse. So there is, of course, much more intelligence behind that. So there are caches from AWS which are much near to the machine which execute Lambda function. And how they did that, simply the snapshot is divided in chunks, 512 megabytes as far as I know. And AWS analyzed how to cache and share them. So they simply find out that these chunks are completely exactly the same for many use cases. For example, everybody uses, for example, Amazon Linux, which is a part of Lambda function. So these chunks can be even shared between all others. There are chunks that every people select Java 21 correct of this. There are people selecting Java 17. So all these chunks may be completely similar between everybody, whereas the difference is the chunks which are connected to the individual Lambda functions. And this other stuff, so what's interesting there is that this AWS doesn't load the whole snapshot during the invocation immediately. It's like watching the video, that the things are preloaded on demand. And that's why these pieces are cached, the standard pieces are cached much kind of near to the function. And the cache will be filled the more we invoke our Lambda function. These function pieces that belongs to the snapshot will be additionally put in, which leads to this, of my observation and what AWS is talking, the first several restores are, the first 10 or something like this, are generally slower than the subsequent ones because the cache will be filled. Yeah, this multi-tiered cache. And this is also why I saw people giving up on Snap Start. They tested only 2 or 3 invocations and say they are slow, but then they have become several hundreds milliseconds quicker with that cache being filled. Amazing technology, to be honest. Yeah, I will personally say it was multi-year journey from AWS to develop like this and beat this cold start. Yeah, but basically, also don't give up. This cache is really important. And once again, to develop this cache, they identified that the cryptography is broken because all restored VMs are the same. So what they did, they provided the interface kind of on restore to restore the cryptographical stuff, and provided the patch for Linux, for OpenJDK, for SSL, which have been accepted. So with that, all these VMs are now not unique anymore. Yeah, so they fixed that, and it's amazing stuff, to be honest, just as a part of technology to provide all those patches, because otherwise it can't work. But of course, that was the link to this cryptography. It was part of the job to restore that, because it's a known problem that then the same VMs are after restore, all they are the same. If you talk to the internet, you break. So because they see it's the same VMs basically. Yeah? So this is kind of one of the things which is really amazing, and we don't even need to know that, to be honest. But this is one of the things why I measured so much. I told you the numbers, but if you measure, for example, not the whole 100 cold starts, yeah, from the beginning, but only take the last 50 values, the P90 will be 100 or 200 milliseconds less, because the cache is already filled. Yeah, so even there is another view. If you don't, just depends, of course, on how many invocations you will have or how many cold starts before the function you will update the function. But basically, the first one will be slower, and you can have so many invocations without updating the function. So you will even benefit more with the time with Snap Start. So that's another kind of amazing stuff.
And there is a fantastic article, a white paper actually from Mark Brooker at AWS that explained that mechanism of how the disk image of a Lambda function of the operating system, the micro VM of a Lambda function, is loaded quickly, and how we managed to get these start time of a few milliseconds or sometimes a second just to load the full operating systems and the JVM and everything. And I was searching for the link while you were talking, but I cannot find it. But I will. By the time this podcast is published, in the notes of the podcast, you will have the link to that article. Thank you so much, Vadym. You're an encyclopedia for Lambda start time and call start and how to optimize. What would be your one advice to developers that are listening to us and learning about Snap Start with you today?
So what's important, I only more or less told you the measurements with a pure Java function without using frameworks. But I'm totally aware there are so many companies which use Spring Boot, for example, or others. And Spring Boot relies really on dynamic stuff. Yeah, there are annotation processing that needs to be done and all this stuff. This, without using Snap Start, it increases the cold start. So my first measurements with Spring Boot, I had the cold start between 8 and 10 seconds, 6 and 10 seconds. So this is because of this dynamic nature of Spring. And of course, I know that the people tried Spring Boot on Lambda function and gave up and say that's even much more unacceptable as a pure Java because it's add-on all that stuff. Snap Start gives you access to that because you can preload the stuff, pre-initialize also before the snapshot is taken. Of course, you will still see that the call starts with Spring Boot will be higher, but they are not then they will be maybe with priming P90 will be 1.2 seconds and not 8 or 10 seconds. It's still possible to use.
So totally acceptable.
Yeah, it's much more acceptable. So you can use Spring Boot on Lambda. You can migrate your application, of course. So this gives you access. Of course, there is a GraalVM native image with Spring Boot support. It's another amazing technology, basically, which can help you to solve that problem. But we are more focusing on Snap Start here. But basically, GraalVM, it's another technology. You need custom runtime for this. You need to build a native image. There are sort of other trade-offs. Snap Start is managed. It's checkbox and everything is managed for you. So it gives access simply for that. Basically, what I say, Java is amazing programming language. I say always the community is amazing. So many open source projects. I'm part of this community since 20 years and I don't want to miss it. Yes, but with that technologies as Snap Start, it gives people access to for Java to the AWS serverless world, where people were hesitant maybe 2, 3, 5 years ago with that cold starts, but now simply try this technology out, measure yourself, but measure accordingly. Just don't give up after 2 measurements. Measure that for the time being. You will see results. You will probably not have the cold starts of Rust. Don't expect that. But the Java is the mature programming language, and it's of cost for people to learn another programming languages. Sometimes it's a barrier. So it gives access for Java. And I see personally with that investment of AWS and that Snap Start technology. And once again, it was probably the journey of multiple years by I don't know how many people with uncertain results. Will they beat the normal call starts? Probably wasn't even known as they started with all the tiered cache and that complexity behind this to give that numbers. And I personally even expect AWS will improve them. They will improve snapshot taking time and they will improve restore time with the time. So we can benefit without doing anything.
And maybe bring it to other languages as well. Java was the first one to focus because this is where the cold start problem is the biggest. But that would benefit Python and other runtimes as well,
maybe,
I guess.
Of course, I'm mainly focused on Java, but I will also explain so I think the problem statement is the same for .NET environment and maybe others. But yes, it's sometimes
everything based on a virtual machines. Actually, everything not natively compiled will suffer from the same. Thank you very much for all your explanation about Snap Start, Cold Start, the different measure you made, how you made it, your observation. And I remember your advice is if you tried already Java and Lambda and you gave up because of the Cold Start time, try again now by enabling Snap Start because it will make a difference, especially if you preload your class with the priming techniques that you explain, and all the links from everything that we talk about are in the notes of this podcast application. Vadym Kazulkin, your head of development at IP Labs, thank you so much for having explained all that and share your knowledge with the listeners of the AWS Developers Podcast. You will hear the next episode of the AWS Developers Podcast next Friday in all good podcast application. But now go build.